Welcome back to eJournal Club, where we turn recent reproductive pharmacology research into 3 minutes you can use. About 1 in 9 babies is born too early, yet we still have no drug that safely calms the inflammation that drives preterm birth. Part of the problem is that we cannot easily test those drugs where they actually need to work. Today's journal is about a high-throughput, 3D printed model of the feto-maternal interface built to discover and develop preterm birth therapies. The paper is from Cherukuri, Kammala and colleagues, published in ACS Applied Materials and Interfaces in 2024. The feto-maternal interface is the border where the mother's decidua meets the fetal membranes. It works as a gatekeeper, controlling which drugs reach the fetus. Finding a drug that calms inflammation at this border means testing many candidate compounds and testing them fast. That calls for high-throughput screening, a setup where hundreds of conditions run side by side. So the goal here was a model faithful to the interface, yet built to run at that scale. The authors hypothesized that a simplified, 3D printed co-culture device, small enough to sit inside a single well of a 96 well plate, could reproduce the inflammatory behavior of the interface while enabling high-throughput drug screening. They designed a cylindrical scaffold with 2 chambers joined by an array of microchannels. One chamber held maternal decidual cells, the cells of the uterine lining. The other held fetal amnion epithelial cells, the layer of the fetal membranes closest to the baby. After testing several materials, they printed the device in a biocompatible resin and coated it with Parylene C to stop it from soaking up cytokines and drugs. The cells were grown inside a gelatin methacryloyal gel. To recreate infection, the team built 3 disease models using lipopolysaccharide, a bacterial trigger on the maternal side, on both sides, and in a 2-hit version paired with a viral mimic. Then, in the main infection model, 2 anti-inflammatory drugs were tested, a Janus kinase inhibitor and a mitogen-activated protein kinase inhibitor. The strengths showed up clearly. First, the device behaved like a living interface. Molecules placed in the maternal chamber moved through the microchannels into the fetal chamber in a controlled way, and the cells stayed more than 80% viable across 3 days. Second, it reproduced the disease. The bacterial trigger raised interleukin 6 and interleukin 8 on both the maternal and fetal sides, matching the inflammatory signature seen in preterm birth. This matters because in preterm birth, it is exactly this fetal and maternal inflammation, not tissue death, that tips the interface toward early labor. Third, it responded to drugs. Both inhibitors significantly lowered those cytokines on both sides, and the platform has already proven its reach. This same device was used to test an exosome-based interleukin 10 therapy, a treatment designed to deliver an anti-inflammatory signal straight to the interface. The takeaway is a low-cost, scalable platform. A single 4.5-hour print run yields about 100 devices for under $5, opening the door to screening large drug libraries against inflammation at the interface. I invite students and researchers to join the discussion on the potential limitations of this model at my Substack community platform. Until then, stay connected and grow together.